Hey everyone, this is Mark Saleh from the Budapest University of Technology and Economics. And in the next few minutes, I'm going to present our paper titled Real-Time Task Scheduling in a FaaS Functions as a Service Cloud. This is a joint work of the HSL Lab Research Group from the university and the Ericsson Research Hungary. Okay, let's start it. This is the overview of the presentation. First, I will start to explain what was our motivation and make it clear why it would be so nice if we were able to run real-time applications in the cloud or edge infrastructures. I also elaborate on what is the real-time cloud in our interpretation and what assumptions we made in our paper. Then I'm going to explain in our opinion what the real-time fast system is, what its components are, and what kind of models we have used. After that, we will see why we should decide precisely where to execute. I mean, on which CPU and on which server execute the real-time functions. I will elaborate on the mathematical problem of this. It's called task partitioning problem and how we solve it in our paper. In the first section, I'm going to explain our evaluations we made, including what the comparison bases are and when our proposed heuristic algorithm outperforms them. And finally, I will discuss the drawbacks of this proposed solution, highlight the future directions, how this work could continue, and conclude our finding of this paper. At the beginning of this project, we asked ourselves how cool would it be if we could run real-time applications in a cloud or edge infrastructure. Does such a platform even exist today? Think about it. The Industry 4.0 remote controlled factories would emerge, where the robots would be controlled remotely. Here, there would be no need for a special purpose hardware like the PLCs, where the real-time controller logics run. If the factory has its own private cloud system, the general purpose servers could perform this job. Another example, by now there are plenty of object recognition models and we can easily download one of them and run on our webcam or another video source to make an augmented video. But it becomes tricky if we'd like to broadcast it live, because the average CPUs have no enough performance to do that. Then how we should decide what kind of GPUs to buy? How much simpler it would be if we simply run this application in the cloud instead of making benchmarkings, deciding which is the best hardware to us. I brought here an example use case where the real-time application execution is essential. Let us assume that we have a traffic camera right next to a highway and we would like to process its recording video, recognize the cars, and stream the video source with these recognized cars live. If we run this car detector application in the cloud, we must consider the processing time of the input video frames, and more importantly, the additional latency of the network between the camera and the application. If the application is not fast enough, that is not working in real time, then just like in this slide, the output video won't be live. That's why we argue that the cloud and or edge platforms should be able to handle real-time executions, thus we could specify the deadline of the car recognition of the video frame to get a live output stream. We have identified that the two major challenges of future real-time cloud systems are the real-time execution of the user-demanded functions and ensuring the real-time communication of them. In our paper, we have dealt with the real-time execution and assumed that the communication happens over a deterministic network. Of course, we are aware of the fact that this assumption is a significant constraint or a missing point of our proposed platform. However, as deterministic networking is an actively researched topic, we believe that this requirement will be increasingly met in the future. We made some assumptions how a real-time cloud should look like. We consider user applications or tasks as functions that is the real-time cloud, actually is a real-time fast system. We suppose applications are controller-like codes, that is, they are triggered periodically. This means input data arrives periodically within a predefined time. Also, in our opinion, a real-time fast need to be a mixed criticality system, that is both real-time and traditional functions should be scheduled on the same cloud hardware. In our interpretation, the real-time fast manages multiple nodes, so it operates on a server cluster. These servers could be heterogeneous ones, containing different type of CPUs, GPUs, memories, NICs, and so on. And finally, as I already mentioned, the underlying network must be deterministic or latency bounded for the real-time applications. Thus, the transmission times can be handled easily. We have defined the real-time cloud in our paper as follows. Real-time cloud is a fast infrastructure, including computing servers and the network connecting them, on which a complete fast software stack runs to offer cloud computing resources for users time-critical or non-critical functions, such that the worst-case response times of these deployed real-time functions are guaranteed to be below the predefined value. Now let's define what the response time means. For the easier understanding, let us assume that we have a classic data center infrastructure on which the real-time fast operates. This function runs in one of the servers of this real-time fast cluster, and the core switch is the ingress point of the system through which the user can communicate with his or her application. We argue the response time of a function includes the time which is necessary for the input data to be transmitted from the ingress point to the target server, plus the time while the function is executed. During the execution, it perhaps makes some synchronous calls of a third-party real-time service, for example, write to a real-time database, plus the necessary time for sending back the response data to the ingress point. And now, let's see what are the components of the envisioned real-time fast system. As I mentioned, it operates on multiple servers, which include multiple like M processors. We depict these processors by pies. The servers are connected to a network, and as I already explained, we assume that this network is working deterministically. The infrastructure also has an ingress point, an interface to the outside world through which a user, for example a robot, can communicate with the deployed function. Real-time fast provides real-timeness behind this point. That is because, for example, if the internet is connected to the ingress point, we cannot take the responsibility for it. The real-time fast itself has an interface through which the users can initiate the real-time or non-real-time function deployment requests. And finally, the most important part of the system is the real-time fast scheduler that decides on which CPU the task should be executed and when. From the literature, we know that functions or tasks in general are modeled by three parameters: the worst case execution time, the period, and the deadline. This model is suitable for the scenario when only a single server exists with a single CPU and the scheduler should choose from a function pool which function to execute. When a function arrives to the function pool, we call that moment to its arrival time. The period gives us the time between two arrivals. Between the time when the CPU starts and finish the execution, this interval is the computation or execution time of the function. Finally, the function, if it's a real-time one, must be executed before its deadline. The non-real-time functions have no such a requirement. But this is not the case here, since instead of a single server, we have a complete server cluster containing multiple CPUs. It is important to differentiate the function and the deployment similarly as the Kubernetes does. The deployment model contains the function to execute and it has the same period that the function has. Furthermore, it has a response time which depends where, on which server and on which CPU the task is executed. The response time can be calculated by the following formula. The C is the computation time of the function, and recall that we must consider the network delay. So the T parameters are the transmission time of the input data from the egress point to the deployment, and vice versa, the transmission time of the output data from the deployment server to the ingress point. And now let's see how we could calculate the worst case execution time of the function. We call the vset is, the vset is depending on the performance of the CPU which executes, and whether it calls a real-time service or not, it depends on this real-time service. The formula of this is here, where the pi is the CPU on which the function is executed. The job is the source code of the function, and the t term returns the time necessary to call the real-time service. For example, if the real-time database and the deployment are located on separated servers, and the function write or read from the database, we must consider the network delay between. And finally, what is the deadline? What is the deadline of a function? In our paper, we assume implicit deadlines, which means that in a single server scenario, the deadline equals with the function period. However, again, we have a server cluster here, so we must calculate it with the transmission times. So they must have enough time to be transmitted. So they are the use models, and I would like to highlight here, I think it's very important that except of the user defined period, all the other parameters depends on the locations and the performance of the CPU on which the user demanded function is executed. And this is decided by the real-time fast scheduler, one of the most important part of the real-time fast system. So the question is how to schedule the functions on the available CPU. We argue in the paper that the global scheduling of multiple hosts is not feasible here because it assumes a single ready function pool. If the pool and the processor are located on separate servers, the added network delay between them would slow down the cluster's computing performance to a level that makes all the system unusable. That's why we use the partitioned ADF model here, which is a static solution, but it can fit well into the multi-node architecture. It has two steps. First, we have to assign the functions to the processors, which will be a static configuration. So if we determine, for example, that task 1 will be assigned to a CPU A, it means that only the CPU A have the right to execute the task 1. And second, on each CPU, we use a separated ADF scheduler. It is a popular scheduler solution since it has a clear and simple math behind it. If some CPU utilization of the assigned functions are less or equal than 1, then the ADF will guarantee that all the assigned function will finish before their deadline. In the Linux, the sketch deadline scheduler implements this EDF operation. Consequently, the question is how to partition the input functions among the available CPUs, and we call this problem as the task partitioning problem. Unfortunately, it is a complex problem, and it is proven to be NP-complete. It has a triplet as input parameters, the number of functions signed by n, we have m CPUs in the set of processors, and finally the big M is the utilization matrix of the user requested functions on the processor. For example, this utilization matrix looks like this, where the columns are the processors of the real-time fast, while the lines belongs to the user functions. One cell contains the utilization of the function on the processor. So, for example, this cell means that if the functions 3 run on the first processor, then it will use the 50% of it. The utilization can be calculated by dividing the vset of the function 3 on pi 1 processor by the deadline of function 3 on the pi 1 processor. These parameters are known from the model of the function. Okay, the partitioning problem can be formalized as an ILP. The objective is to find a feasible partitioning using the least number of processors of the given function set such that their deadline requirements are met. We minimize the number of processors to use for the real-time functions in order to give the remainings to the non-real-time ones, thus preventing them from starving for CPU. We have two constraints here. First, task must be assigned exactly one host, and second is the schedulability requirement of the EDF. Since real-time task partitioning is an NP-complete problem, we have created greedy type heuristic algorithm to assign real-time functions to the minimum number of processors. I wouldn't dig into the details. I think we have no enough time for that. The concrete steps of the proposed algorithm are in the paper. Final part, the evaluation of our proposed partitioning algorithm. First, we had to find the rival solutions to compare with. It was more complicated than we thought first, since to the best of our knowledge, currently there is no cloud platform which could run real-time functions too. Additionally, current multiprocessor scheduling research works typically assumes that CPUs are in the same server machine. Thus, they are using different constraints and objective functions. Finally, we have found a solution that we call BR in the followings. This is an LP relaxation of the original ILP problem and aims to return a feasible partitioning that uses as many CPUs as possible to minimize the maximum cumulative utilization. One might notice that this objective is quite the opposite of what we aim for. So we have extended it to direct it to find the minimum number of the CPUs that can execute the real-time function. We call it EBR, and it has the same input than the original problem. And in the first step, we sort the CPUs according to maximum how many functions can be assigned to them, according to the EDF schedulability type. Then we start a for iteration in which in each iteration we call the original BR algorithm with the first I CPUs in the sorted list. And if the BR returns a feasible solution, we stop the iteration, and that's the return value of the EBR2. The third comparison solution is the FFD, the first fit decreasing beam packing heuristic algorithm. We have chosen this because if the values in each row of the utilization matrix are identical, then actually we get a beam packing problem. Where the CPUs are the bins, the functions are the items, the utilization of a function is the size of that item. The size of each bin is 1, and we are looking for the least number of bins where the items can be put. First of all, we have examined when the algorithms cannot return valid task partitionings. The colors show how many tasks we have to assign. The y-axis shows the percentage of the simulations when the given algorithm could not return a valid task partitioning. So the less percentage we have, the better for us. The x-axis shows the density of the used utilization matrix for the simulation. And the definition of this value is the following. It is the value that specifies the average of the maximum percentages of the functions that can be assigned to a processor according to the EDF schedulability. I know it's quite complex, so let's see an example. Let us assume that we have a utilization matrix like this. To the first CPU, maximum 3 out of 4 functions can be assigned, which some utilization is less or equal than 1. This means that maximum 75% of the task can be assigned to the first CPU. This value is 50% for the second CPU, and to the third one, all of the functions can be assigned. We call the average of these percentages to the density of the utilization. Our proposed algorithm, depicted by OG, always return the feasible. On the second place, maybe the EBR could be, since from 6% density, it also always gave back valid partitioning for each task input. In our second evaluation round, we examined how many processors were used in the function assignment. And please recall, it is a minimization problem. We want to use the less number of CPUs to run the real-time functions. Here, the colors mean the examined algorithms. The y-axis are the average number of the used processors in the results, while the x-axis shows the density of the utilization matrix used in the simulation. We can see that always our algorithm, the blue one, used the fewest number of CPUs in the assignment. But as we have increased the number of tasks in the simulations, the EBR also approached this result. In the case of 500 tasks, the two were almost the same. So, if the algorithms return valid partitionings, then OG and EBR use the fewest CPU. What about the runtime complexity? The classical bin packing heuristic FFD is the fastest, followed by the proposed OG, and finally arrives original BR solution, and just after that arrives the EBR. And finally, interestingly, we have examined the corner case when the CPU utilizations of the functions do not depend on which CPU they assigned. In this corner case, each row of the utilization matrix contains the same values, but the rows could include different ones, and as I said, this is equal with the bin packing problem. In the upper part of the figure, we examined how many times the algorithms gave back valid solutions. OG and FFD always were able to return. The bottom part shows the goodness of the algorithms, that is, the number of the used CPUs in the output partitioning normalized by the task count. As expected, since this problem is equivalent to the bin packing problem, the traditional offline heuristic algorithm FFD performs the best, followed by OG, EBR, and BR. To conclude our work, OG is the only algorithm that always found a feasible partitioning in our simulations. OG also resulted in the fewest number of processors for partitioning, and we have to know that EBR was also effective. It provided similar results as OG for large number of tasks. In terms of runtime complexity, EBR lagged significantly behind from OG. And using homogeneous utilization matrices where the partitioning is equivalent to the classical bin packing problem, FFD gave the best outcome since it is designed for this problem, but all came in the second place. Currently, deterministic underlying network is a strong constraint of this work, but it is a well-researched topic nowadays. In the future work, we would like to examine how to enable it in the real-time FaaS system.